All right. That way we have plenty of time to catch up and get everything done we need to get done, and we won't fall behind. So that way the exam will still cover chapters 7 and 8, which we should have plenty of time to finish over the next 3 days. Because if I remember correctly, today is Tuesday. Okay, good. So I'm not that far off. Okay. Homework. For 7 and 8. I don't see any reason why 7 couldn't be done. I could push 8 back to Monday, but I think I'll leave 7 where it is. I don't see any reason. I think that one, we've already covered all that material, so you should be able to finish that one as of today. All right. So, any questions from the homework before we get started, by the way? Especially out of chapter 7, if you had any. We haven't gotten through a lot of 8 yet, but no? Okay. So, today, what I'm going to do is we're going to finish, we're going to keep going to chapter 8. So last time we picked up, we were looking at this concept of the central limit theorem. We saw some data to sort of support this, though we didn't necessarily justify this particular quantity, so I'm just going to state it and tell you that's how it is, because that standard deviation is what we know to be true. So the idea is basically, it really doesn't matter what distribution you're drawing data from. If you take enough samples and you average them out, that average behaves really nicely. It happens to have a nice normal distribution, and it also happens to be nice and centered around the true mean, because it's your best estimator. This right here is the standard deviation, and you notice as n gets big, so if your population has a fixed standard deviation, as your sample size gets big, what's going to happen to your standard deviation of your sample mean? The variability, it's going to go down. It shrinks, right? So the more samples you take, basically you can be more confident that that sample mean is kind of zeroing in on the truth, right? Because ultimately, as you approach the population size, you're getting closer and closer to that. I mean, by the time you sampled the whole population, then you know exactly what the mean is, right? So you're getting closer and closer to that truth. All right, so that's what we had finished talking about yesterday. So let's look at some examples here. All right, so I'll give you an example. If you look at the eruption times for Old Faithful, then if you look at the time in between, so like how long you gotta wait. So like if it goes off once, how long do you have to wait for it to go off again? So if you look at the time in between, then the mean is 85 minutes, and the standard deviation of those is 21.25 minutes. So it's not particularly consistent. Okay, it has an average of 85 minutes, but that's a pretty big standard deviation, 81.25, right? So that means you could end up sitting there for 100, 140, 160 minutes. Wouldn't be uncommon, or maybe less too, okay? So it's pretty variable, all right? So if for example, I just wanted to know, let's say that you're just going to sit there and you're just going to, let's say you go once and you're going to observe, say, one eruption. So you're not looking at sampling a bunch of them, just one, right? So if that's the case, then what would be the probability, so this isn't working with the sample mean yet, what would be the probability that you're going to have to, say, wait more than 95 minutes? What's the probability that you're going to have to sit there for more than 25 minutes and wait for this thing to erupt again? So you show up like right after it just erupted and you missed it. You're like, dang, I missed it. So I'm going to have to wait. So now we got to think about, okay, well, how what's this probability? Okay, let's say that it's normally distributed, right? So the eruption times are normally distributed with an average of 85, standard deviation of 21. how could we calculate this probability that you're going to spend more than 95 minutes waiting? What do you think? Yeah, because we're looking for, it's a normal distribution, right? It's centered at 85. Here's 95, and we're looking for this upper tail probability. So what do we need to do? We need to get a z-score and go to the z-table to do this calculation, which I just realized I don't have my z-table up. That's okay, I'm going to need it later. Okay, so if I do that, so the z-score, 95 minus the mean over the standard deviation, what do you get for that z-score? Round to 2 decimal places. 0.47. Other people that get that? Maybe? Anybody else got a calculator out? I believe you. I just like to have confirmation. 0.47 sounds reasonable to me. It's just a little less than half. Yeah. So here's your z-score. So we need to go to the z-table and look up the probability that a z-score is greater than 0.47. Now, how do you do that? How do you do an upper tail probability? There's 2 strategies. Are there not? We can get the probability below and do 1 minus. What's the other way we could do it? We could go get the we could just go get the low tail probability of negative 0.47. So either one works. All right. So I need to pull that up though. I should save a copy of that in the course document so I don't have to do this every time.
Wait, can you repeat that?
Well, yeah. So there's two strategies to doing this because the probability of being above 0.47 is the same as the probability of being less than negative 0.47. They're the same. So you can actually look it up both ways. So we can go get the 0.47 and get this value and do 1 minus. I usually just go get lower tails because it's faster. So anyways, let's go back here. And we need to go back to our appendix. And does anybody remember what page it's on? I think it was like 11. So right, hey, there you go. So if we go to, here's our z table. I'm going to scroll to negative 0.40, 1, 2, 3, 4, 5, 6, 7. Boom, there it is. 0.3192. 0.3192. So it looks like this is going to be 0.3192. If you go look up the other side of the table, then you would probably, if you go look up positive 0.47, it would be 0.6808. It would be the complement of that. So then this is the probability. So if you just show up like right after Old Faithful goes off, there's a 32% chance you're going to sit there for more than 95 minutes. Okay? All right. Any questions about that example or how we got that one particular? No? Maybe so?
Yeah, I missed how you got 0.68.
If you were to look up, and if you were to go to the z-table, so we have our z-score is positive 0.47. So right now I'm on the negative side. So if I go over to the positive side, let's go to 0.47. 0.01, 2, 3, 4, 5, 6, 7. There it is. You get 0.6808 on the positive side. I happen to look up the negative side, but you can do it both ways. Okay, because remember the distribution is symmetric. So the probability in the top tail is going to be the same as the probability in the bottom tail for the negative z-score because of the symmetry. So I looked up this tail, the bottom tail, and I just knew that it would be the same as this top tail. But you can do it both ways. Right? The only reason why is because the z-table automatically gives us less than probabilities. So I just always, so then you get it directly. You don't have to do the 1 minus. Yeah.
What would be a question? Well, this question, but what is this called?
Well, this is calculating probabilities with a normal distribution. So this is actually a chapter 7 practice. Okay. Because this is what we were doing in chapter 7 was dealing with normal distributions and calculating probabilities associated with things that come from normal distributions. Okay. But that's not really what I want that's not what we're so interested in chapter 8. In chapter 8 now, we want to look at what happens when we're not just doing this once, what happens when we take a lot of samples. Okay, so let's keep this with Old Faithful in mind here. Go ahead.
So without stat crunch and the Z table, how will we find it on like a hard copy test?
I didn't use StatCrunch for this one. I just used a Z table. What do you mean?
Yeah, like when we don't have a Z table, like how are we supposed to calculate this?
Oh, you're supposed to memorize the Z table.
You're like hilarious.
No, I'm just kidding. I'll give you a Z table. Yeah, I'm sorry. Yeah, I'll give you a Z table.
Because I'm like, okay.
I'm sorry. Yeah, I should maybe have clarified that. Yes, I will absolutely give you a paper copy of the Z table for the exam. I usually when I'm doing my job, I usually print out copies and bring them. I moved offices and I can't find my old copies, and I just haven't printed out new ones yet.
Are they all the same?
But yes, they are. If you look up a Z table, you have to be a little careful because some books are really dumb and they do the areas wrong. Anyways, it doesn't matter. Yes, 99% of Z tables are identical though.
So there isn't a formula that I should be memorizing?
No.
Okay.
No, but what I would recommend doing, because apparently I'm not going to print these off, I don't know, but is you can just go to your book and print them off the book.
Okay.
Just go back in the appendix. It starts at A11, and shoot, where's that button to get me out of this thing? How do I get out of this view? Stupid. All right. Oh, there we go. Probably that. Yeah. You can just hit print up here, and then it'll actually allow you to print. Say, print how many pages. You can just say I want to print 2 pages, starting right here, and then you'll get your Z table out, and then you can carry it along with you. But I'll give you copies during the exam. Okay. All right. You could memorize the Z table if you want.
I have it.
Probably wouldn't work very well though. Yeah. But yes, great question. All right, so Old Faithful. All right. That was with the mean was 5, and the standard deviation was 21.25 minutes. So now let's say I'm not just talking about like one instance. Okay. Let's consider in a day. Okay. Let's say that in one day. There are, say, 22 eruptions. All right. So what I want to know then is what's the probability that the average of those 22 eruptions exceeds 95 minutes? Well, really, we're looking at the wait times here, like how long between the eruptions, right? So I want to know if it goes off 22 times in a day, what's the probability that the average wait time exceeded 95 minutes? Now, it was pretty likely that just going there and sitting down for one observation that we would have to wait more than 95 minutes. Do you think it's as likely that the average of 22 eruptions is going to exceed 95 minutes? I'm seeing no. Why not? Why not?
I think as you add more data
Mm-hmm.
and average it out, everything's going to kind of move more towards the center.
Yeah, that's what we would think, right? Because we saw with our data set, as we took more samples, our sample mean actually gets closer to the truth, right? And so, there it goes again. But anyways, so here, when you just do one observation, there's a lot of variability. You might end up waiting a really long time or not a very long time. But when you start averaging out a lot of observations, you should start to see, hopefully, things kind of coming towards the mean, right? There's going to be less variability because you're going to get some small times, some big times, they're going to average out. All right, so what we need to do here is we need to use the central limit theorem, right? So the sampling distribution of the sample mean is going to be what? Well, what's it going to be? What should our sample mean be centered around? It's supposed to be centered around the true mean, which we know is 85 minutes, right? So it's still going to be centered right around 85 minutes. We saw that with our data yesterday. Even after we sampled those girls at the clinic, their heights were still centered around the true mean height. Okay, but what's going to happen to the variability of our mean? Well, the variability is going to go down. It's going to be sigma over the square root of your sample size. So since we're sampling 22 people, okay, what's that good? What's it going to do? 21.25 divided by the square root of 22. What do you get? Decimal is fine. Let's round it to 2 places. Why not? 4.53? 4.53? All right. So notice the mean of 22 samples is going to be a lot less variable than just a single observation. And that makes sense. The more data you take, you would hope you're going to see less variability. Right? The more you look at, the better your guesses are going to get. Okay, so now when we're looking at calculating this probability, we're not going to calculate our probabilities based on the old distribution like we did last time. Okay, we're not going to do that. We're going to calculate our probabilities with our new normal distribution. Yeah? So here's what we're going to do. So the original distribution, right, it was centered, if you're just doing one observation, it was centered at 85 with a standard deviation of 21.25, so this would be like 106.25, right, and that. But we didn't do that. We took 22 samples and calculated the sample mean, and so our new distribution, it's still centered at 85, but now its standard deviation is only 4.53. So this would be 89.53, right? So our old one was a mean of 85, standard deviation of 21.25. After we took a bunch of samples and averaged them, now our mean is going to be still 85, but our standard deviation is decreased to 4.53. Yeah? So our sample mean actually comes from a different normal distribution. It's a normal distribution with less variability. Okay, now notice this is going to change our probability, because on our original distribution, when we were only doing one observation, where was 95? 95 was down here really close to the mean, right? That was our original distribution. But on the sample mean, where is 95? Where is 95? It's like up here, right? Because one standard deviation up would be 89.53. Another standard deviation up would be, I don't know, something else, whatever. Decimals are hard. So, but the point is, it's going to be farther out, okay? 95 is going to be farther out. So is our probability going to be more or less likely than it was when we were only observing one? Less, and it should be, because we're taking a sample mean. So, but the process is exactly the same. So what are we going to do? We're still going to get a z-score. We're still going to go to the z-table, and that's where we're going to get our probability. The difference is now, to get our z-score, it's going to be 95 minus 85. That doesn't change. The thing that changes is the sample, is our standard deviation, because now we're drawing from the distribution of the mean, not the original distribution. Okay. So what does that z-score come out to be? I think it's going to be more than 2. 2.21? Yeah. So now it's a z-score of 2.21. So that's the z-score we're going to take to our z-table. And that's the probability we're going to count. Now, you can go to this. You can look at it on the positive or the negative side. I'll just see where my table's at. My table is at the negative side already, so I'm just going to stick to that. Whoa, hey there. So negative 2.21. negative 2.201. There it is there. So 0.0136. 0.0136. So this is 0.0136. So this is 0.0136, which means if you looked up positive 2.21, you should get something like 0.9864. Right? Okay. So this is the answer right here. 0.0136 would be your solution. So even though when we were only going to do it once, there was a pretty high chance that our wait time would exceed 95. If you average a whole lot of eruptions, there's a really, really small chance that the truth, or that the mean is going to exceed 95. Okay? All right. So the key is, if you're only observing one thing, then you can use the original normal distribution. Okay? But if you're going to observe multiple things and average them, you can't do that. You need to use the updated variance, or the updated standard deviation, which is going to be the standard deviation divided by square root of sample size. Right? What would happen if we took more samples? What would happen to this standard deviation? It's going to go down. Down, 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 down. Because n gets bigger. Okay? All right. Any questions about that one? So it's the same as chapter 7. There's just like this preliminary step where you need to actually get the new standard deviation. Okay. All right. Now the nice thing about the central limit theorem is we said it doesn't actually matter what the original distribution was as long as you take a large enough sample size. All right. So I'll show you another example here. One common application we look at a lot in statistics is wait times, like queue times, like how long it takes for something to get done. This has a lot of applications in consumers, like businesses' wait times, but it also has applications in like computer science, internet applications. How long does it take to queue something? So let's look at a simple example. So wait times at, say, a drive-through. Okay, so like at Wendy's or McDonald's or something. So the wait times at a drive-through, they have a non-normal distribution. What do you think the distribution of wait times looks like at a drive-through? I think it's skewed to the right, meaning what?
People wait longer.
Most people wait longer, or most people wait less?
Less, yeah.
Most people wait less, but occasionally you have people that have to wait a long time. Skewed right? I think so. Okay. So wait times at a drive-through have non-normal distribution with a mean of, let's say, 59.3 seconds and a standard deviation of 13.1 seconds. Okay, so this is known over a long period of time and a lot of data. All right. So so say you're a manager or you're some sort of corporate person, and maybe you're a manager at a branch, and you know this. What you want to do is you want to see if maybe like you think your night shift crew isn't fast enough, right? You think like they're not performing up to the standards of the rest of the working population, right? So what you do is you test that. You say, I think it seems like my night shift is going too slow. I want to test that. So how would you test whether or not you believe they're not working fast enough? What do you think? How would you do it? So what if that's your job? I say your job is to go figure out if the night shift at this restaurant is going too slow. How would you do that? You would sit in silence. And then you would be fired. You got to do something.
I'd probably quit.
I would quit. I'll give you a raise if you do my data analysis. How about that?
How big's the raise? Where did we start at?
Well, we can negotiate that. Okay. But your job is data analytics for this fast food chain, You need to go see if this night shift is up to snuff. So how do you do it? What do you do?
Start recording times in the morning.
Okay, so you start recording times, and you go there. Let's say you go there at night, right? You go to the drive-thru, you order something, you see how long it takes them to deliver. Yeah? Are you going to do it once? No. How many times are you going to do it? You're going to do a lot, right? You're going to do it more than once, and you're probably not going to do it all on the same night. You're going to randomly select times and orders, so you're not always going to order the same thing, right? So you randomly select times, randomly select what you're going to order, and you just go a bunch of times, all right? So let's say you do that, okay? So let's say your decision is you decide to randomly visit, let's say 40 times over the course of some whatever, okay? So basically, you go there 40 times. Each time you randomly select a time during the night shift, and you randomly select an order on the menu that you're going to order, and you go in, you order, and you time your wait. Yeah? Okay. And once you've gone 40 times, what are you going to do? You have all these wait times together, so you might look at the average. Yeah. So you're going to go there, you're going to go 40 times, you got 40 wait times, you're going to average them out, and then what are you going to see? What are you going to look at? What are you going to compare it to? Okay, well, so all right, so I'm kind of assuming that we kind of know overall how these restaurants behave. Like, for example, we already know up front how the restaurants behaved historically, right? We know historically they've had mean wait times of 59.3 seconds and a standard deviation of 13.1. So what would you compare the sample mean to probably then? What? Yeah, you would say, okay, I know that over time, this restaurant has always averaged 59.3 second wait times. So I went and sampled 40 orders. It took them this long on average. So you would probably compare it to 59.3, right? Because that would be a good measure of whether or not they're performing similarly to the population, to the restaurant as a whole, right? Okay. Now, the question, though, is, what if you go through this drive-through and you get an average wait time of 60 seconds? Is that problematic? Is 60 seconds? If you go through 40 times, your average wait time is 60 seconds, are you prepared to go back to that night shift and say, hey, you guys are too slow?
No.
Why not?
Oh yeah, go to less than once. Need to pick it up.
So you would. Okay.
Oh yeah.
But what people who say they wouldn't, why not? Yeah, it's pretty close, right? I mean, maybe you just happen to order a big order. You just happen to go on a night when they were down. I mean, you don't know, right? Your random selection mitigates some of that, but just by random chance, sometimes they're going to underperform and sometimes they're going to overperform, right? That's just going to happen sometimes. So what we want to do is we want to get an idea of, okay, how likely is it? So let's say you do all this, and the result of your sample is you calculate, say, a sample mean of 61.5 seconds. They're all fired. You're all fired. Harsh. That's harsh. Okay. Whoa. There's got to be something going on. This thing's getting on my nerves. Yeah. I'll look at it later. All right. So, are you concerned about the night shift or not? No? Yes? No? Maybe so? Because I'm not worried about them because they're all fired. Yeah. So, should you be worried about them if this is their average? Okay, but what if they're always, I mean, if you think about this, if they're truly performing like, say, 2 seconds slower on every single order all the time, is that a problem?
Yeah.
Could be. I mean, 2 seconds slower when you're going through thousands of orders a day, thousands, tens of thousands of orders a week, hundreds of thousands of orders a month. Is a 2 second delay an issue? Maybe.
Yeah.
Could be. All right, so one way to measure this is you say, okay, all right, before I go out here and fire them all, okay, John, you've already fired them, but I probably wouldn't yet. Before I went and fired them all, or had a talk with them, I would look, okay, so the true mean is 59.3. Now, we took a lot of samples, which means our sample mean, according to the central limit theorem, it should be approximately normal because we've taken 40 samples. That's more than 30. And they had some result up here. This was their result. It's above average for sure. Now, the question is, how likely, the question I would ask is, okay, well, how likely is this to happen just by random chance? And the way we can measure that is we say, okay, well, let's see. Let's see, how likely is it that just by random chance, it would take them 61.5 seconds, even if they were performing up to snuff. They were performing just like everyone else. All right. So this is what we will calculate. I want to know what's the probability that the sample mean would exceed 61.5 seconds. That's my question. All right. And that'll give me some gauge of whether or not I should be concerned. Because if something like that is really likely, then I shouldn't be that concerned about them. If something like that is really unlikely, then I should be concerned. Okay, so how would we do this calculation? What do we need to know? Yeah, so this is the population standard deviation, but I actually took 40 samples. So what we need to do is we need to get the sampling distribution. Of the sample mean. Okay, so the central limit theorem tells us that x bar should be approximately normal because we took a big enough sample, right? And what would the mean be? The sample mean should come from, the mean should be centered around what? The true mean? Which was 50, what was it? 59.3. And the standard deviation should be equal to the population standard deviation over the square root of the sample size. So that was, the population was it 13, what was it? 13.1 seconds. And I sampled 40 people this time, okay? So what is 13.1 over 40? Let's round it to, say, 2 decimals. 2.0? 2.05? 2.05. Other people get that? Yes, no, maybe so.
Got 2.07.
2.07? 2.07? I'm getting more agreements on that one, so I'm going to go with that. All right, 2.07. Okay, so then that tells me that my sample mean, it's coming from a population, the sample mean is coming from a distribution centered around 59.3 and a mean of 2.07. That's assuming that they're just behaving like everybody else. Okay, so then how could I actually get the probability? You know, here's 59.3. Here's their results was what, 61.5? Or 8? Was it 5 or 8? Was it 61.5? 61.5. Oh. Okay. All right, so how do I get this probability now? What do I need to do? We got to get a z-score? Yeah? Okay, so the z-score is going to be 61.5 minus the mean all over the standard deviation. Okay, and what do you get for that rounded to 2 decimal places? 1.06. Other people with that? Okay, so then I'm really looking for, I'm going to go to the z table and look up 1.06 and get the probability of being above 1.06. Or you could look up below negative 1.06. Okay, so if we go over here, I'll go to negative, it's just easier. Negative 1.0123456. 0.1446. 0.1446. Okay. That's going to be your answer. So does that seem pretty likely? I mean, is it pretty likely that you're going to just see stuff in that range just by random chance? 14, 15% of the time? Does that seem unusual? What does your book kind of use as a cutoff for things we deem unusual? 5% of the time. So stuff like this, even if that crew was performing exactly like everyone else, their sample mean is going to be 61.5 or more, like 14, 15% of the time. That's not that unusual to me, right? That doesn't concern me so much. All right. So that, to me, that seems not so unusual. So I'm not really ready to go in there and say, hey, you're all fired at this point. You might be willing to. Okay.
They're already hired new people.
Well, see, that's a problem now because they're probably way slow.
Not that.
Okay, but you can imagine, right? Eventually, it would hit a point where you'd be willing to say, no, this is not random chance. You guys are really too slow, right? We need to work on this. Something's going on. Okay. So once, say that your sample mean hits, 63 seconds, 64 seconds, 65 seconds. Eventually, you're going to hit a point where you're going to say, nope, enough's enough. We're not dealing with this anymore, right? Okay. Any questions about that? Okay. So again, just like the last example, it's the same. We're still using z-scores and z-tables, but we have that preliminary step where, because we're taking the mean of many observations, we need to get that sample standard deviation before we go calculate probabilities. All right? And you need to use that updated standard deviation for your z-score. Okay. Sound good with that? Any questions before I move on? Because we got lots of fun stuff to do. Okay. All right. So the sample mean, is that an example of a statistic or a parameter? Sample mean. It's a statistic? I think so. So remember, you have this idea of, you have your population versus your sample. Okay. And so far, we've looked at some quantities about your population and sample we're interested in. For example, one thing we looked at was averages, means. So the population mean we call mu. The sample mean we call x bar. Right? What's another value we've looked at that we've dealt with? In fact, we just dealt with it in the last problem. Standard deviation. That's another something we've looked at. So the population has a standard deviation. We call it sigma. But of course, our sample data also has a standard deviation. We call it S. And that's something we've learned to calculate. Okay. Now, there's another statistic that we commonly look at, and they're looking at them a lot right now, actually. It's a number that you can report about a population or about a sample. It's not the mean, but it's what? You guys actually, your first activity dealt with this type of number. Say what?
The average?
That would be the mean. We talked about the median. No, I'm not thinking of the median, though. What's a number that you see reported a lot in surveys or articles? Or it's not average, not the median, but what? What's that? Not the mode that often. Not the variance. They report it a lot right now because we're going into elections. Polls report what? They usually don't report means. They usually report what? Not frequencies. They report what? What do they usually report? What's that? Not well. They might report you the total. Like how many people they sample. True. Yeah, they report percentages, right?
Oh wow.
We got there eventually. Okay? Proportions or percentages, right? So sometimes we're not interested in an average, right? Like I'm not there. And the average isn't applicable if you're talking about like voting, right? I can't like look at the mean. How would you even do that? You can't look at like the mean votes for a person, right? What you have to look at is you look at what makes more sense is look at the percentage that are going to vote. So the proportion. There is a true population proportion, like in the sense of an election. There eventually everyone that's going to vote is going to vote, and someone's going to get a certain proportion of the vote, right? It's a true population proportion. We call that P. But of course, leading up to the election, we can't possibly sample the whole population. So what do we do instead? We take a sample and we say, hey, who are you going to vote for? And then from that sample, we calculate proportions. And the sample proportion, we call that P hat, because it's like a P with a hat on it. P hat. Right? Yeah. Yeah. This hat indicator is actually usually an indicator of an estimate. So when you see little hats on characters, it usually means that was estimated. It's not the actual value. The bar we use, shoot, I don't know why. But anyways, so there you go. Okay, so this is what I want to focus on now. I want to shift for a second away from means and look at, okay, well, what if we're not interested in estimating means? What if we're interested in estimating proportions or percentages about a population? Okay, and it's going to change things a little bit. All right, so let's look at an example so we can collect some data right here on our own class. So let's look at in our class, let's see, what kind of things might I be interested in knowing percentages about you guys? What's something you want to know? Let's not get political. That never turns out nicely. What's that? Okay, sure. So say you wanted to know, I want to know what percent of my students in this class work full-time. Okay? So how many people are in here right now? So let's count. Don't count me. I'm not a student. So I got 32 as well. Anybody else get 32? Okay, so there's 32 people in the class. How many people in here work full-time? That is, what's considered full-time? Is 30 considered full-time?
32.
I had no idea.
Yeah, 32 or more hours.
32 or more hours. Okay, so how many people in here work full-time? Okay, so raise your hand high because I got to count you. Okay, so we got 1, 2, 3, 4, 5, 6, 7, 8. Did I get everybody? 8? Okay, so 8 work full-time, and we're defining full-time as 32 or more hours. Okay, and we have 30 students total. 32. If I write it big enough, it'll go away. I don't know. Okay, 32 students total. All right. So then, if we treat the class as the population, then what is the true proportion of students who work full-time in this class? 8 out of 32? Which is that exactly 1/4? Oh, nice. So we'd say 0.25. Yeah. There goes my computer again. All right. So exactly 25% of us work full-time. Okay. Now, of course, what would happen, though, if just like the mean, what's going to happen if I'm not allowed to sample everybody in this room? What if I'm only allowed to sample 5 people? Okay. So if I was only allowed to sample 5 people from the class, okay, what's going to happen to my sample proportion? So let's say I pick, I'll do it like I did yesterday. Maybe I only pick the the people going down in the beginning of this row. So I sample 5 people. So we'll start up here. So Trey, how many do you work full time? Okay. So that's a no. Do you work full time? Do you work full time? Do you work full time? And do you work full? And you don't. Okay. So there you go. So in that row, what's my sample proportion? It's just 1 out of 5, which is 0.2. Is my sample proportion equal to my population proportion?
Pretty close.
It's close. Okay. What if I take another sample? Okay. And I just go along the back row of the, this is not random, but let's say I just go along the back row of class. So going along the back row, starting back there, do you work full time? Okay, Greta, do you work full time? Greta? Okay. No? No? No. And Greta, I just realized I called you Emma the other day, but that's because I have an Emma Ellis in one of my other classes. I'm sorry. Okay. Your p-hat is 0 out of 5, which is 0. Is that close to the truth? No. Okay. So what's going to happen every single time I take a new sample? It's going to change. Are some of them more likely than others to occur? Yeah, like, is it really likely that you're going to end up with 5 people who all work full time? Is that going to be very likely? Could it happen? It could. It's not likely, though, because there's only 8 of them out there. All right? So you're going to have to pick almost all of them to get a proportion of like 100%. It could happen, though. Okay? So what I want to do is I want to see, okay, well, what happens when we just look at sample proportions? Okay. So here's what I want to do. I'm going to look at this stat crunch, kind of like we did yesterday. So StatCrunch has this nice tool where I can actually simulate data like this. So we have I can basically make a bunch of you guys, sort of. What I'm going to do is I'm going to do these Bernoulli or binary trials, and I'm going to say, let's simulate like your class, but let's say that there's more of you, like there's like, I don't know, 100 students or something. Let's make it 1,000 all in one column. And so what I'm going to do here is I'm going to say simulate data that has a 25% chance of occurring. That's what I want to do. Okay? All right. And I want to do that. So what it's going to do is it's just going to generate, I think, like a bunch of zeros and ones, right? So it just generates a whole bunch of zeros and ones. And you can figure out the proportion that you could, I could average these out, since the zeros and ones are the actual observations. If I just look at the mean, you can see in this column 0.249 of those observations are successes, basically. So all the ones are people who work full time, and all the zeros are people who don't. Okay? And apparently like 24.9% of them in this particular random sample. So here's a class of 100 people where basically 25% of them work full time. So what I want to do then is I want to do like yesterday, I want to sample from this. So let's say I pick from my actual students, but I'm only allowed to pick 5 of them. Okay? And I'm going to do this, say, maybe 100 times so I don't kill my computer like I did yesterday. Okay. And so it's going to produce a whole bunch of samples. So the first time we sampled, we got nobody who worked full time. The second time we sampled, we got nobody who worked full time. The third time we sampled, we got 2 people who worked full time. All right? And so now I'll go back to my, do like yesterday, I'll do column statistics. From all of those samples, I'll calculate their average, which is equivalent to their proportion of successes. Store that in the data table. Cool. Alrighty. So let's say I need to delete that now. Edit columns, delete, take out everything I don't need anymore. And actually now I'm going to rename that. So these were the students, right? And now this is, we'll call it p hat with n equals 5 samples. Cool. All right. So if I graph that, I want to look at what that looks like, the histogram of those proportions. What does it look like? Does that look to be relatively skewed or not? It's pretty. It's kind of, I don't know. What do you think? Skewed? Not skewed? Is there really any shape to it? It's hard to see. There's not much there. Does it look normal, really, though? Does it look normal? I say no. Okay, so it's looking kind of weird, but that's also because if we only calculate 5 people, there's not very many options for p hat. It can either be 0 or 1/5, 2/5, 3/5, 4/5, 5/5. Now, as we take more people from this pool of students, let's say instead I look at 50 students. So each time I do 50 students, all right, and I go ahead and do the average of those students, or the proportion of those students. Sort of my table. Okay, thank you. And get rid of the stuff I don't need, so I don't need all this junk. Ooh. Okay, then we're gonna, now this right here, this is gonna be p hat when n equals 50, right? 50? All right. So now I'm going to look at the histograms. I'll look at both. This was when I only took 5. This is when I took 50. What do you think is going to happen? Anybody want to guess? That would be cool if it did. That would be great if it started to look normal. What do you think? It's looking pretty normal. Normal-ish. Yeah? Does that look pretty normal to you? Ish? Let's do it one more time. I got just a few minutes. Let's say I do this one more time, but I take more. Let's say, so there's only 100 people there, so let's say I take like 80 samples from each, and I compute that. Okay. I do stat, summary, stats or columns, mean. I want all of these. Okay. And I want to delete all those columns I don't need. That would be all of these samples. Thank you. And then I look at, this is p hat with n equals 80. All right, so now let's see. Graph, histogram. Sample of 5, sample of 50, sample of 80. Let's stack them all up on top of each other. Huh, what do you know? How's that? Looks pretty normal, doesn't it? Yeah, and now where is it centered? Where's the center of that normal distribution? It's pretty much right at exactly 25%. Yeah. Okay, so we're going to come back to this tomorrow. But the moral of the story is, if you take a big enough sample, even proportions start to behave normally. And they're centered right around the true proportion, too, so that's pretty cool. All right?